You could say hello to her.
Say our class today.
Say, hi, Maria. Hope you're doing well. And if somebody watches this video years later, they'll be like, who in the world's Maria? Wow, okay. Well, in any event, wow, notice I've changed the problem. I do have an original problem here, but I wanted to change this. Notice what's happening. If you have a graphing calculator, you could tell me where you've got extrema. You could look for high points. You could look for low points. And all of a sudden you look here, you'd say, well, I'm going to do that. Well, what if you can't? What if no calculator is allowed? Calculus will still show you where extrema occur. Wow. Tell you what, let's break it down here. We're going to say, first, I want to take a derivative. So I've changed this problem to x squared minus 4, bump it up to the 2/3 power. And you know what? Help me with the derivative. What rule do we need to do, guys? Chain rule. Thank you. We're going to bring the 2/3 down. We're going to have x squared minus 4. And my new power is going to be what? Negative 1/3. I'd subtract a 1 from it. Then do what? Multiply by 2x, the derivative of the inside. So everybody okay with that? All right, so let's clean it up a little bit. I'm going to say, all right, we've got f prime of x, and this 2 gets multiplied with this 2. We'd have a 4. Down below we have a 3. I have an x up here, but this is a negative exponent, so I'm going to bring this down to the denominator and just write it as a positive exponent. That's my derivative. Everybody okay? So my first step is to find the critical numbers. Find the x values where this derivative is 0 or where the derivative is undefined. So there are two things that we are searching for. Wow, let's think about this. I want to know where f prime equals 0. What does that, if I have a fraction, what makes a fraction 0? The numerator or denominator? The numerator, right? We're going to look at this numerator right here. You know what? I'm interested in when 4x equals 0. I could divide by 4, and I'm going to get x equals 0. Okay? Because, hooray, we're done. Well, not quite. Not quite. We also have to look at where f prime doesn't exist. Where f prime doesn't exist. That's where the denominator equals 0. Now, guys, at this point, I'm going to streamline this just a little bit. How would that highlighted green expression have to hit 0? What's really going to have to happen? X squared minus 4 has to equal 0. Would we agree with that? Kids will say, well, it's the whole thing. Yeah, and you could write that out if you want. I mean, you could do this right here. You could say, hey, I've got this thing equaling 0. Really, at the end of the day, you're saying it's what's inside of that 1/3 power that we are most concerned with. And now, what do we do next? Solving, we're going to, we could add 4. And then what? Plus or minus square roots. Wow, you're going to get plus or minus 2. By the way, you could have factored the left side if you wanted to. Difference of squares, you'd see you'd get the same answers. We doing okay? So as we were speaking earlier, we're saying, hey, these critical numbers are here. Maybe it's a maximum point like I had on the board. Maybe it's a minimum. But then again, maybe it's this crazy situation where, you know what, it actually is neither. Just because your derivative is 0, just because your derivative is undefined, does not guarantee that you will have a local max, local min. You've got to do some work. And what did the note seem to imply that we're most looking for? We're looking for, how would we know we'd have a local max or a local min here? Like, let's start off, a local maximum. What's going to have to happen? F prime changes. We're going to do a number line test. Do a number line test. You'd say, you know what? I have 3 critical numbers. And I want to test that into my derivative. Because I want to know when my derivative is positive. I want to know when my derivative is negative. And if I can see a change in the sign, you are going to be able to know what type of an extrema you have. By the way, this becomes exceptionally visual. I hope you're going to see that in just a moment. Look, from -2, look, we don't have a closed interval. We're from -2 to -infinity. Let's test something. What do you want to let x equal? Be good to yourselves, though. -10 is certainly okay. I'd recommend -3. If you did -10, you'd get full credit. I'd choose -3 just because it's small, right? And so there's more than one way to do this. But guys, here's f prime. Here's f prime. So I'm going to say that's 4 times -3. Down below I'll have 3, and I'll have -3 squared minus 4 to the 1/3 power. Now, right now, this could get scary because kids will say, well, if I don't have a calculator, Mr. Dobner, how in the world can I know what's really happening? Well, -3 squared is a 9, and 9 minus 4 is 5. What do you think? Is this positive or negative? Negative. The numerator became 4 times -3, right? The denominator, really it's a cube root down there. That's the cube root down there. -3 squared, when I plug -3 in here, it becomes a 9. 9 minus 4 is 5. That's the cube root of 5 down below. Wow. Well, hey, that's all nice. Tell you what, for f of x, please do this. This is going down. Look what I just did, please. Look what I just did. Now it's going to become very visual. I'm saying f prime is negative. That means f is decreasing. The curve should be coming down. Hey, I want to test something between -2 and 0. What do you want to test? -1? By the way, could you test something else? Could you have tested decimal? Yeah. And what am I doing? I'm coming right back to this definition, this one right here that I'm putting the star on, this f prime. That's what I'm plugging -1 into. Now, kids will say, it's negative, Mr. Dobner. I can see already. Careful. Careful. Look, it's 4 times -1. Down below, I've got my 3. But now it's -1 squared minus a 4 to the 1/3 power. So yeah, I've got -4 up on top, but this -1 squared is a positive 1. 1 minus 4 is -3. So here's why we're slowing it down a little bit. Wow, what's going on with -3 to the 1/3 power? Well, guys, tell you what. If you need to, you can use a calculator real quick to get some help here. Look at this. If I did -3 and it's the cube root, I hope you know that there is a cube root right here. Can that even exist? Seeing kids shaking their heads no. Maybe that's a big question. Oh, wow, maybe this doesn't exist. Actually, yeah, it does. Think of it this way. What if I gave you the cube root of negative 8? Cube root of negative 8, you're saying what number times itself 3 times is negative 8? What do you think? Negative 2. Look at that. Negatives are allowed inside of cube roots. So what am I getting at? Down here, this is a negative. Up on top, that's a negative. What's the overall sign? Positive. And then it's going up. Okay? So from here, we still have to check 2 more. We still have to check 2 more. Don't think for a second. Please hear this. I've seen this happen. Kids will go, oh, Mr. Dobner, we all know what happens. It alternates signs. Negative, positive. The next one's negative. Maybe. But look at this picture here, please. Look at this picture here, please. Tell me about the tangent line slope right now. Positive or negative? Positive. Tell me about over here. It didn't change, did it? You have no guarantee that those signs change. And that might be one of the biggest misconceptions that kids get. They'll say, oh my gosh, this is tedious. I'm having to plug all this in and check it. Yeah, I know. It's not the funnest thing. But listen, just double check it. You plug in a 1 right here. It's 4 times 1, right? And down below you'll have your 3, and then you'll have 1 squared minus 4, and you've got your 1/3 power. Ooh, tell me about this. Positive or negative? Negative. And kids will go, whoa, wait a minute, Mr. Dobner, hold on a second. The top is positive. Yeah, but the bottom's negative. The bottom is negative. Look, you've got 1 squared is 1. 1 minus 4 is negative 3. So it's the same thing that we just saw a moment ago. It's really like the cube root of 3. That means your curve is going down. Hey, one more thing. Guess what we can test? Maybe let x equal 3. And what do we get? A 12. And this is 9 minus 4. That's a 5. Tell me about this. What do you think? What do you guys think? Positive. Now, right now, that extension of what I drew up on top is going to show you what has just occurred. Look at what's happening at x equals negative 2 for a second. You'd help me out here. Is that going to be a relative max or a relative min? What do you think? It's going down, then it's come. Oh my gosh, do you see that? That's a min. That's a low point. That's why I want you to draw those little direction bars above. It is so visual. The number line will guide you. You just got to make sure you're carefully checking. And I'm picking something out. Not everything is this tricky to check. Dealing with negatives inside of cube roots, yeah, that gets to be a little tricky. You know, if you can just have everything straightforward in a polynomial, it's going to be easier. Look, you're going up, then you're going down. Oh my gosh, that's a high point. You see that? Then you'd say, look, I'm going down, and then I'm going up. Oh my gosh, that's a low point. You don't even have a graphing calculator, and now you know what's happening. Holy cow. Holy cow. This is just the beginning. This is why calculus can be unbelievably powerful. And this is what we could call quantitative analysis. Quantitative analysis is when you look at a real-world problem and you'd say, hey, actually, I'm going to try to determine what to do by running some numbers and using some mathematical models and see where it leads us. Qualitative analysis is like, well, I feel this, and it looks like studying this would be a good practice. This gets way more particular. you can say, hey, I think we should head this way because the numbers show that we would yield the greatest profit. We'd be having the smallest cost. That type of thing. Is that making sense? Let's put it together then. Let's put it all together. Right now, kids will probably go, well, okay, so how do we finalize it? Here's what you got to do. They're asking for the extrema. There were 3 critical numbers. All 3 of them came into play. So I'm going to come over here. By the way, I'm crossing out the problem down below. It's really just a review problem. And I'm trying to streamline our lesson so that we're covering the most ground. We had the assembly last time. Definitely want us to be able to review some stuff from last week too. But look at this, x squared minus 4 to the 2/3 power. That was the original function. I'm seeing that there are 3 x values that I am very, very, very interested in. What are they? -2, 0, and 2. That's what's really coming into play. Say, all right, well, what do we do? Well, plain and simple, plug them in and see what you get. You plug in -2 into this function here, you're going to get -2 squared minus 4 to the 2/3. -2 squared is 4. 4 minus 4 is 0. 0 to the 2/3 is 0. It won't take too long for kids to say, oh my gosh, that last one that you've got, Mr. Dobner, it's the same thing. Do you see what I'm getting at? If I'm going to plug in a +2 squared, hey, that becomes a 4. 4 minus 4, you just get a 0. Well, this is where we're going to have to earn our money. This thing right here, and this is why I changed the problem, because occasionally when we see this, like if I give you just all polynomials, it's not so bad. This stuff is involving some roots, and that gets kids uncomfortable sometimes. So you'd say, well, how do I deal with this thing right here? I plug in a 0. And, oh, wow, Mr. Dobner, this is like 0 squared. It's gone. I've got -4 to the 2/3. And I don't know, can I just write it like that? Well, I guess you could, but listen, if I just gave you -4 squared, what's -4 squared, guys? 16. And then if I said you had a 1/3 power, what's that? The cube root. You know what this thing really is? It's the cube root of 16. It's the cube root of 16. You see a 3 down below, that means you've got a cube root. You're taking a cube root of something. And then you'd say, well, I've got -4, but I still have that 2 up there. The 2 is telling you to square it. And -4 times itself is 16. So, wow, we've got 3 different y values that are super, super important. Right now, I want us to refer back to the picture above and see if we could address it. What's happening when x was equal to -2? What did we have? We had a local min. And the same thing at 2. Would we agree with that? The picture showed us that. Here's what we're going to do to justify it. We're going to say there's a local min of 0 at, well, there were 2 x values. Tell you what, we could even streamline it. We could say x equals plus or minus 2. So the template is talk about what kind of an extrema you have. Say it's either a local max or a local min, but name the y value. That's so important. When I talk about minimum values or maximum values, those are y values. That's so important, I'm going to say it again. When you're talking about absolute min value or minimum values, maximum values, always, 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 those are y values. Pardon me. P214. Good, how are you? Wow, I'm just about finishing up a lesson. Can I send them down after those? Okay, great. Thank you so much. Okay, bye. Okay. So, tell you what, you got to also give a reason. Please hear this. Please hear this. You got to give a reason. The College Board is requesting that you write it in a certain style. So you could say the local min of 0 at x equals plus or minus 2 because f prime changes from, and guess how it changed? Look at it. At -2, f prime changed from negative to positive. Okay? So they are requesting for you to always write that sentence. About 10 years ago, they made a big change. They used to allow just the number line to justify the work. And then about 10 years ago, I got probably like 50 emails throughout the year, and they said, warn your kids that talking about maximums and minimums, you can't just refer to the number line. You got to write a sentence. And, we've been doing that ever since. So if you get to the scoring rubrics, you'll say, oh, yeah, why are they always writing that? They're mandating it, but that's really what the first derivative test is saying. There's a change in the sign of the derivative. Okay, is this making sense so far? Let's finish this up. There's also a local max. And you could say, well, just from that number line right there, wow, I'm looking here. Here's your high point. But remember, if I'm saying there's a local max, I better name the y value. Local max of, what's the y value? Cube root of 16. That's right here. At what x value? At x equals 0. And then we can say because. Now, I could say because f prime changes from positive to negative. Let me show you another way you could write it. And you need to see both. I'm going to say because f changes. F changes from increasing to decreasing. That's the alternate way you could justify a local max or a local min. You could say, rather than saying my derivative is changed from positive to negative or negative to positive, you could say f is changed from increasing to decreasing or vice versa. We doing okay with that? All right. So, listen, there's one last little part here. Oh, and by the way, maybe let's also just real quickly take a look at this. Where do you think f is increasing here? Sometimes that's all you're asked to do. I'm going to maybe put part B right here. F is increasing on what interval do you think? Yes. Very good. Excellent, Rudva. Excellent. -2 to 0 with closed brackets. Kids will say, how do you know that? Well, that's where your derivative is positive. So we can say f is increasing there. You could put a union right there, and you could say, oh, it's 2. Now, here's the one time you're not going to put brackets. Infinity is just a concept. You can never really reach infinity, and that's why we'll never put a bracket around infinity. Is that making sense? How about decreasing? Ooh, what about this interval? That interval right there, I even gave you a little bit of a hint if you look at the number line. What do you think? Negative infinity. It's always a left-right connotation. When you look at your number line, you go left number, right number, and you write them in that order for interval notation, right? And then we're going to say, well, there's also somewhere else. Where else? 0 to 2. You could get questions just on that. We doing okay? All right, we're covering a lot. You know what? We've got to talk about something else, though. And we're just going to do one more example. But the second derivative. The second derivative, kids will say, this is the second derivative test. Yeah, honestly, it's not. It's not the second derivative test. That's something later. Whoa. Oh, my goodness. Our screen just went haywire. There. Wow. Well, that's a big relief. Holy smoke. Wow. Well, in any event, the second derivative, what does the second derivative talk about? Concave up and concave down. Kids might look at that and say, what in the world is that? Concavity is the curvature. Not only can you learn where a curve might hit high points and low points, you can even know from calculus what type of curvature or bend the function has. Please write this down. Concave up is like a cup. Concave up is like a cup. You might say, what do you mean by a cup? Look at the bend there. That curve would be bending as if it could hold water, right? And then you'd say, well, wait a minute, you didn't talk about concave down. Yep, concave down is like a frown. It looks more like that. The kids will go, why in the world do you ever want to know that? Well, it's one thing for me to tell you the curve is going up. It's another thing for me to tell you other information, but now you even know the bend of the curve, the curvature of it. Wow. Well, look at this. Concave up is going to be if your second derivative is positive. And it does mean that your tangent line slopes are actually getting bigger. We'll talk more about that next time. We've got a lot to digest right now. Concave down occurs when your second derivative is negative. Wow. And then the point of inflection. A point of inflection occurs when there's a change in concavity. You're going to be continuous, but there's a C. If you'd say here's where a point of inflection might be, it's where your curvature changes. You move from being up like a cup to being down like a frown. And kids might say, give me a picture. That sounds so weird. Look, here we change. You see that? The curvature just changed. Wow. Well, last one. Tell you what, we're just going to real quickly just see, and by the way, with calculus, we could actually even sketch this thing. This is so much easier to do a first derivative test. But listen, let's just find inflection points if we could. That means take your first derivative, so much easier. We dealt with the hard stuff just a moment ago. Help me out. What's your first derivative, guys? 3x squared minus 3. Help me with my second. Yeah. And guess what? I'm going to set 6x equal to 0. The kids will go, why did you do that? Well, this is a candidate for an inflection point. We don't know yet. We really don't know. To have an inflection point, we need to see a change in the second derivative. Notice that common theme of the day. A change in the sign of a derivative. Either the first derivative for extrema or the second derivative to help you with inflection points. So, wow, as we're looking at this, you might say, are you going to do a number line? Oh my gosh, yes we are. Look at that. We're going to say, there we are. Yeah, Kyle. Inflection. Inflection point. Sorry. I abbreviated that. Thank you for raising that. A lot of times you might see a teacher or professor do that. INF. It might look like infinity at first, right? And that can get a little confusing. But yeah, let's bring this on home. You could say, well, I guess we're going to test. Yeah, less testing. It's easier. What might we test? Maybe test x equals, what do you think? -1. Here maybe test x equals +1. And you know what you're testing? You're testing f prime. F double prime, I should have said. F double prime of -1 is 6 times -1. 6 times -1 is -6. You've got a negative value. Tell me about f. F is concave down like a frown. Everywhere from -infinity to 0, the shape of that curve is kind of like a frown. You say, oh, okay. Well, let's check what's happening at 1. You'd say, well, hey, if I plug in a 1 here, you go 6 times 1, well, that's a 6. That's positive. That means we're concave up like a cup. So I just drew you a picture of an inflection point. The inflection point is where the curvature changes. And please understand how much information you're getting from the calculus. You're not using the graphing calculator. Amazingly, you could you could find the critical numbers right now. We could have set this equal to 0. What are the critical numbers here? If I set the first derivative equal to 0, it would just be 3x squared minus 3 equals 0, 1, and -1. There'd be 2 possible candidates for local max and local min. We'd do a number line test and we'd figure it out. You wouldn't even have a graphing calculator. You could tell me what this looks like. That's pretty cool. When you really think about what you can do now, it's flat out amazing. And calculus can show you hidden behavior. Behavior that maybe you wouldn't even see on the graph necessarily because you didn't zoom in enough. Wow. Cool stuff. You can tell I love this stuff. All right. Well, tell you what. You'd say, well, do you have an inflection point? Yeah. Well, if you've got a point, you better tell me the x comma y. So I'm going to say, hey, we've got this thing right here. And I'm going to plug in my 0. Some of you are going to be like, oh my gosh, I could just do this in my head. What do we get? 1. So I'm going to say, is there an inflection point, guys? Yeah. Look, I'll abbreviate it this time, Kai. Inflection point at 0, 1, but let's justify it. Because you could write 2 reasons. And you need to know how to say both reasons. What's one? If somebody say, well, how do you know there's an inflection point there? You don't have a picture? Yeah, I know. Why? What's going to happen? Yeah.
Does the second derivative changing from
Yeah.
positive to negative?
Because f double prime changes from negative to positive. So good. Well said. Well said. Now listen. Here's the last thing. We could have said, or because f changes from what? Not negative to positive. Concave down to concave up. Wow. Look at that. Look at that. That's pretty cool, right? Really, really cool stuff. So, listen, what I'd like to get to you, this is such an important lesson today. It's, I think you can see the power of what you have now. You can do so much. So we're not going to watch a video for next time. Most of this is honestly review. There is some new stuff. It's problem 1 and problem 2, and they ask you to pull it all together. The rest of this is honestly just some review. So, to get this all out to you guys. What's that? Oh, thank you so much. Yeah. Let me stop this video.